Okay, get this. What if I told you that we could create some serious cold, like enough to freeze water, just by stretching a piece of metal? Now, that sounds like something straight out of science fiction, right? But it's not. It's actually the key to a technology that could completely change how we cool, well, everything. And to really get why this matters, let's start with something that's probably humming in your kitchen as we speak, your refrigerator. It has a dirty little secret, and you're about to find out what it is. So here's the secret. It's not about what you're keeping inside your fridge, it's the chemicals that do the cooling. These things are called hydrofluorocarbons, or HFCs for short, and they are shockingly potent greenhouse gases. And I'm not just talking a little worse than CO2. Their global warming potential is literally thousands of times higher. It's a massive problem. Now, this whole environmental headache comes from a technology that's been the standard for over 100 years. It's called the vapor compression cycle. And yeah, it's the workhorse of modern cooling, but it's totally running on borrowed time. You'll find this system everywhere. Your home's air conditioning, your car's AC, and of course, your fridge. It all works by compressing and expanding a gas to move heat from one place to another. But the big issue, the fundamental problem we have to solve, is its total reliance on these chemical refrigerants that can leak and on noisy compressors that just waste a ton of energy. So, the big question is, how do we get away from these gases and compressors? Well, believe it or not, the answer starts with something you've probably fidgeted with a million times. We're talking about the simple rubber band effect. You can actually try this yourself, right now. Go grab a rubber band. First, just touch it to your lip to feel its normal temperature. Okay, got it? Now, stretch it out really fast. See, you can feel it get warm. Then just let it go slack. It feels noticeably cool against your skin. That simple little feeling, that's the key to this whole revolution. Okay, now imagine taking that simple rubber band effect and putting it on steroids. Instead of that tiny bit of warmth and cool, you get a temperature swing so huge it can actually make ice. That, my friends, is the science of elastocaloric cooling. It just uses special metal alloys instead of rubber. So how in the world do we turn this idea into a real cooling system? How do you stretch a piece of metal and make a refrigerator out of it? Well, the magic is all happening down at the molecular level. The absolute most important thing to remember here is that the elastocaloric effect is a solid-state technology. What does that mean? No gases to leak into the atmosphere. No loud, clunky compressors. Everything happens right inside a solid piece of metal called a shape memory alloy, just by applying and releasing a little bit of stress. So here's where the real magic happens. It's this super fast, totally reversible change in the metal's crystal structure. When you stretch it, the atoms literally have to realign themselves. They shift from this relaxed state, it's called austenite, to a more rigid, tense structure called martensite. It's that physical snap between states that forces heat out of the material. To turn this into a working fridge, we use a 4-step cycle. Okay, step 1, the loading phase. We take our alloy, maybe it's a wire or a thin plate, and we stretch it. This forces that phase shift we just talked about, and boom, the metal gets hot, just like our rubber band. Next up, while that alloy is still hot and stretched out, we pass a fluid over it. Could be water or even just air. This fluid absorbs all that heat and carries it away, getting rid of it into the surrounding room. It's kind of like what the warm coils on the back of your current fridge do.
Then comes the coolest part, and I mean that literally. We release the stress on the alloy. It snaps right back to its original shape, its crystal structure flips back, and in doing so, it sucks in a ton of energy from its surroundings. This makes its temperature plummet way, way below room temperature.
And finally, the absorption phase. That now frigid piece of metal is exposed to the space you want to cool down. It just sucks the heat right out of the air inside your refrigerator, chilling your food and drinks. And then the cycle just starts all over again. Loading, heat transfer, unloading, absorption. Over and over. Okay, this all sounds pretty amazing, right? Clean, efficient, silent cooling. So the obvious question is, why don't we all have one of these in our kitchens right now? Well, like with any game-changing idea, there are some pretty big engineering hurdles we have to get over first. It really boils down to 3 main challenges. First, there's material fatigue. You know how if you bend a paperclip back and forth enough times, it eventually snaps? Same idea. A fridge needs to survive millions of these stretching cycles. Second, it takes a whole lot of force to stretch these metals, which means you need some pretty powerful and bulky machinery. And finally, there's this thing called hysteresis, which is basically a tiny bit of energy that gets wasted as heat in every single cycle, and that slowly eats away at the system's efficiency. And this really shows the kind of trade-offs that researchers are wrestling with. So on one side, you've got nitinol. It's kind of the gold standard. It gives you a huge cooling effect, and it's incredibly strong. The problem, it's really expensive and needs an immense amount of force to work. Then on the other side, you've got copper-based alloys. They're much cheaper and easier to stretch, but they tend to break down and fail way sooner.
But you know what? Those challenges are exactly where this story gets really exciting. Because the breakthroughs that are happening right now, that's what makes this a true revolution. And the solutions are just as clever as the technology itself. And you should know, this isn't some fringe science happening in a dusty lab. The U.S. Department of Energy has looked at all the possible alternatives to our current cooling tech, and they have singled out Elastocalorics as the single most promising path forward. That is a massive vote of confidence. So here's how we're starting to crack those problems. Researchers are using 3D printing to create these amazing, intricate honeycomb structures that can distribute stress way more evenly. This drastically improves how long the materials last. And on a micro scale, they're creating super thin films of these alloys to cool computer chips directly. Just think about it. That could be the end of loud, whirring laptop fans forever. And let's just take a step back and remember why this is all so critical. Cooling already eats up a staggering 20% of all electricity used in buildings across the entire globe. So making that process more efficient and completely getting rid of harmful refrigerants, that's not just a nice-to-have. It's an environmental necessity.
This quote just nails it perfectly. Think about the shift from those big, hot, fragile vacuum tubes to tiny, solid-state transistors. It completely changed the world and created the digital age. Well, we are on the verge of that exact same kind of leap, but for cooling, moving from clunky gas systems to elegant, solid-state metals.
So, as we look to the future, the real question is this. Is the future of cool silent? A future without the constant hum of a compressor in the background, powered instead by the quiet, efficient, and clean stretching of metal? You know, based on everything we're seeing, that future might be a whole lot closer than you think.